My name is Mindy. I work for Docker, which is why there is a ASCII picture of a whale on my title slide. So here's a brief overview of what I'm going to talk to you about in the next 35 minutes, hopefully a little short so we'll have time for questions. I'm going to give a quick overview of the kinds of monolithic traditional operating systems I want to present these library operating systems in contrast to. I'm going to talk about what I mean when I say library operating system. I'm going to show you an example of a library that we might use in one. I'm going to show you what it looks like when we compose all these disparate parts into a composable library or network operating system. I'll talk about how we might know whether the thing that we've created is any good, whether we might actually want to use it. And I'm going to talk about how we can use this technology to reject the default reality and substitute our own, and take the power of operating systems coding into our own hands. So, by way of contrast, the way that we traditionally think of operating systems looks something like this. We have our user-level application, which probably relies on some kind of external libraries. We generally have these things written in the same language as our application. We have some API that we use to communicate with some lower level bits, our runtime, maybe some shared libraries that are shared across all kinds of different applications on our system. And then we have things that we want to ask the kernel to do for us. The kernel being this great big piece of bunches of different stuff that I have all slotted together right here. The interface between our application and the runtime that we're running our application in is constrained by what this monolithic operating system wants us to ask, and how this monolithic operating system wants us to ask it. Usually the examples that we interact with on the application layer are things like sockets. So if we want to, for example, write to a network or read from a disk. We also have, you can also imagine these in terms of system calls, and there are a huge variety of syscalls that we might want to communicate with the kernel using. And then just for a bit of completeness, so I'm not accused of lying to you later, all of this, I'll be talking about all of this as if it runs on top of a cloud hypervisor. It doesn't necessarily, but I'll talk about it as if it does. And we'll also talk about all these things as if they're running on top of silicon bits, because I'm not really a theorist. So if that offends you, I apologize. So I want to look a little bit more at this interface between our application and the kernel. Oh, by the way, I'm an OCaml programmer, so I'm going to be talking about an OCaml library operating system called MirageOS. Most of the things that I'm going to say about library operating systems generally also apply to HalVM, which is a Haskell library operating system. Is anyone here affiliated with HalVM, or have they worked with it? Or? Oh, cool, I can say whatever I want. Awesome. So if you're more a Haskell person than an OCaml person, there's hope. You can still work on this cool stuff without having to invent your own thing. So, but getting back to what I was saying about APIs and communicating between your application and the kernel. This is a little code snippet from the OCaml, from the way that OCaml basically wants you to interact with sockets as a way of interacting with the kernel from your application layer code. So we can get a socket, which is basically, we can imagine it as an abstract type that we use for this sort of communication by basically passing some information about how we want to communicate, a socket domain, which is just what sort of communication do I want to do, a socket type, which is what kind of network I want to talk on, an optional type that isn't typed as optional. It has the implicit semantics that if you pass 0, that means none. And gives you back something called a file descriptor. And then you have another call called connect that takes a file descriptor and some description of what you want to connect to, and as a side-effecting operation, makes that file descriptor that you passed in do something if you call something else with it. If you've done a lot of programming in a language that has nicer affordances for doing stuff than this probably seems really gross to you. It seems really gross to me. Just to be honest about that. What this really is some C written in OCaml, because the This is what our underlying C kernel expects. It expects a wad of bytes. It expects some numbers. And it wants to go off and do some stuff that it doesn't want us to care about. It wants to express whether or not that worked with, at best, a number, and possibly setting some error information out of band somewhere else. This is particularly bad in the case of connect, because connect is the kind of function that very frequently doesn't work for reasons that have nothing to do with our program. Like we're trying to connect to a host that's on the network, and the network is offline. Or we're trying to connect to a disk, and the disk isn't there. And we would really, really like to have a better interface for finding out what happened than just maybe an exception was thrown or something bad happens and your program crashes. But we don't have a whole lot of choice for how to interact with this, because if we want to talk to the network or if we want to write to a disk, if we don't want to write our own drivers, we have to have the operating system do it for us. So how can we get better interfaces? If we take the stack that I showed you earlier and we change it up a little bit so that our application is running on top of a whole bunch of different libraries that are also written in the same language that our application is written in, all of which are running in a runtime that's then running directly on the hypervisor, we suddenly have access to changing all sorts of things about the interfaces between our application and the various things that need to get done. So in this model, the things that I need from the operating system, they might be networking or storage, timekeeping, some interface to entropy for gathering randomness, possibly for cryptographic purposes. All of that stuff, I specify when I write my application that I need it. I specify when I'm assembling my application where I want to get it from. And then when it runs, all of these things that I've specified, that I've either specified implicitly or that I've chosen which expression of the implicit stuff I want, all of that is compiled in with my application as a bundle. You can imagine this as being somewhat analogous to building a static binary if you're in the business of caring about linking. Another nice side effect of this is because this library code is written in the same language as my application, I'm more equipped to do something interesting with it. So if I'm in a traditional monolithic kernel environment and there's something wrong with one of my drivers, my recourse is basically learn an entirely different style of programming from the kind of programming that I'm used to doing if I'm, say, an application level OCaml programmer. Figure out what the problem is, figure out how to patch the problem, figure out how to test that I've patched the problem, possibly figure out how to upstream my patch to the problem, which God help you. And then possibly deploy my patch, again, God help you. But if these libraries are in something that I'm used to interacting with, I can use all of my usual tools. So I can use the testing tools that I'm used to using. I might be able to build and test stuff in user space, which is enormously useful. So that all sounds amazing, right? Like you're super pumped. So let me show you a little bit of what a library might look like, so that you can possibly be convinced that this is something that looks better than sockets. So just a quick explanation of what we mean in Mirage OS when we're talking about these different things. We have interface definitions for various common operations, like checking the time or getting a random number, send a packet, write a file, all those kinds of things. And then we have specific modules that fulfill those module types. So we have some particular implementation that knows how to write a file in whatever file system or send a packet or whatever network. And when you build your application, you say, my application needs something of type network, and it needs something of type clock. And you can also do some specification on, I want this particular kind of clock, or I want this particular kind of file system. So here's a very shortened but very honest expression of one of these module. This is a signature from one of the module types that we have in Mirage OS for file systems. We have a read function and we have a write function. That's cool. That's stuff you might want to do with files. But you might notice that we instead of having like an exception-based way of getting our return information or error information from these kinds of functions, we are actually using the capabilities of our language to get error information in a polymorphic variant. We can do things like, say, define a custom type that says, okay, the chunk of memory that you send to this thing has to be page aligned. We can actually take all of these things that are implicit requirements of interfaces of things like sockets and lift them up into the type system, so that when we compile, we know that, I've sent to write some memory that I haven't scrubbed first, and that's a really bad idea because heartbleed. We can also imagine doing things like having a lot more information in our error message, like having a variant that contains the actual chunk of possibly unparsable data, for example, if we're doing some kind of parsing, or excuse me, or some information that we might want for backtracking. It's not necessarily the case that you couldn't build this kind of interface on top of sockets, but it is a really, really huge pain to take the poor interface that you're given with a monolithic kernel and possibly enhance it with a whole bunch of out-of-band information. I personally find that much less satisfying than the idea that I can write my own interface that tells me the things that I care about. So this is just a nice little bit of OCaml for those of you who are annoyed that you haven't seen enough bind operators in the past 10 minutes. This is just an example of what some actual code that's implementing something like read looks like. It takes a set of arguments that, they look pretty reasonable. You're reading something, you want a file system to read it from, you want a path. That's where your file is. You take some offset parameters. How many bytes do you want? It's arguable whether you might want to say that or not, but I'm not arguing that this is the best possible API. I am arguing that it's nice that you get to pick your own. If you're conversant in OCaml, this looks like very boring code, and I think that is a feature and not a bug. I personally really want to be able to understand what my operating system is doing when it's doing things like this. So how do we take these things and make them into an operating system? This is a sort of signature level explanation of what it is that we do when we take a whole bunch of specifications of libraries and implementations, and we want to make them into something that we can run. In MirageOS, we usually talk about this in terms of a unikernel because that's the more interesting deployment story over a Unix process. But in our framework and in a couple of others, it's equally possible to make a traditional application as it is to make one of these single address space things that runs directly on a hypervisor. So what we do when we compose these things is we take our application code. We can imagine this is our business logic, our web application, our thing that scrubs our database of everybody's social security number, whatever it is that we want. A list of dependencies, so my application needs to talk over a network. A list of implementations. My application in the environment that it's going to be running will need to talk over Ethernet. That's great. And some kind of output, something that we can run. Something that's interesting about doing this is that once your libraries look, once your operating system drivers look just like libraries, as I said earlier, you can use all of your normal debugging and testing tools on them. This is a tweet from Antti Conti, someone who wrote a similar system that takes the NetBSD drivers and makes them into a library operating system so that you can build all of your code linking in the C libraries in NetBSD. Some things are just much easier to do in this framework. I'm going to show you next a little bit of test code that we use in MirageOS for doing some simple testing of the TCP stack. So this is, again, some very boring looking OCaml code. We make a buffer. We fill it with some bytes. We define a couple of functions that are useful for testing. We say, okay, this particular This particular variant means that we need to send a selector back. That's great. And we're just going to go through, call the function that we have under test, which is options.marshal, do some checking, return, we're done. And because we've defined this in this way, we can run all of the tests that we have written for all of our networking code directly in user space. We could run this, for example, in Travis CI to see whether all of the stuff that we've written from the application code all the way on down to passing packets to what's presented to us as a physical backend is working the way that we expect. So we can use this from unit tests to integration tests, which, if you've ever tried to wrangle hardware to do kernel testing, is a very, very nice thing to be able to do. We can even take this code and run it in a REPL if we want to interact with it in real time and see what changes we can make, see what crashes, see what doesn't crash. Another thing that we can do is, instead of taking someone else's implementation, we can use our own implementation for whatever our evil or otherwise purposes may be. So this is our compose signature from earlier. We still have our application. We still have a list of dependencies that we need. We need some implementations, and we're going to make some kind of output. In this case, I've decided I want to make a unikernel. But when I call this, instead of using some implementation that's bundled with the library operating system, I've written my own. And there are a number of reasons that you might want to do this. So, for example, you might have some code that it does different things depending on what the current time is. And there are a number of different ways that you could test your userland code that cares about time. You could hard code in sometimes that you're worried about doing the wrong thing with. You could change the system clock, which is a pretty annoying thing to be doing, for example, on your dev machine when you're also trying to talk with other people or keep your appointments based on what your calendaring app wants you to do. By the way, I recommend not setting your computer the date on your computer to be February 29th all the time if you want to ever make it to meetings. But with this, you can very easily test your code in the environment where it's always February 29th, 2000. Here's a slightly more interesting example that uses a little bit gross OCaml code. Those of you who don't like global state, sorry, global state. So all this is an implementation of the clock module type that we have in Mirage, which basically just wraps the actual clock that we might get from the hypervisor and says, okay, every time I'm called, I'm going to remember what time it was last time I was called. And I'm going to accelerate the amount of time between the last time I was called and now by some amount of time, by some constant. In this case, it's time reduction factor. So basically, this is a clock that's going to run real fast. And if you have a lot of code in your application that is doing things like setting expiry times or doing long waits, this is really useful for just being able to run that code in user space, see whether it does what it's supposed to, and not have to wait 2 hours for a test run. You could also do this by changing a bunch of constants in your code and mocking out a lot of stuff, but then you're not testing the code that you're going to be running in production. If you do this, your application code is the same as it was. It's just the system that's doing something different because you've told it to. Also, a really fun thing to do with this is make clocks that go backward. Because this is something that happens sometimes if you have a machine with a lot of clock skew and you're checking with NTP, and the NTP daemon suddenly realizes, oh my gosh, my clock is 2 seconds ahead. I'm going to set it backward, and then everything in your application explodes. If you want to catch this before it happens, this is a fun way to do it. So there are a bunch of other things that you can do that we haven't tried yet because this is a fairly new idea, at least for us. Some thoughts that I had: you could have network interfaces that always have new packets waiting. So basically, this is a network interface where you are always getting slammed with new information, and you can see how the things that you've written deal with that. You can also have network interfaces that always lose packets or always reorder packets. You can have random number generators that read from a constant list. So for example, if you have something, if you have some input into your application that's meant to be random, like you're always generating new user IDs, that's really annoying to mock out for pretty much the same reasons that time is. But you can just say, okay, every random number that you call in this application, read it from this list of pre-generated random numbers, and then compare your output to the static output that you're expected to have. And suddenly your testing just got a ton easier. You can make entropy sources that always block to mimic environments where you might not have access to a whole lot of entropy. Like if you're running in a server in a rack that doesn't have access to a keyboard or a mouse, doesn't have any kind of outside of itself conception of reality to provide any kind of entropy. You can see whether your application does what you expect in that environment. File systems that are always full. Lots of applications fail when your file system is full. As a person with a very small SSD, I can tell you this for sure. It would be real nice if everybody tested their code in that environment. Block devices that are always busy. DNS that is always hijacked. The possibilities are endless because there's an endless set of things that can go wrong. And I want to make it easy to test every single one of them. Here are some wilder thoughts that I've had. So our application presumably has some kind of state in it, right? Like most of our applications have state. Sorry. That's why they have to pay us and pay computers to manipulate stuff. It's rough, but what are you going to do? So often when we're debugging, we are trying to figure out what about the state of the thing that we're debugging caused some bad situation that we see. So in a monolithic kernel, we might have to run user space tools that know how to interact with the kernel's view of its own internal state. We might be able to do something like hunt around and proc for information about what's going on. We might be able to run single commands that say, okay, here's the status of your ARP table, for example. We might have a write interface to that information, and we might not. So even if we have some suspicion of some internal kernel state that might be contributing to what our application is seeing, it might be really difficult for us to be able to create that and verify whether or not our hypothesis is true. But we can do better with library operating systems because we have access to these libraries, and we can say, I would like to replace a library with one that is going to show me its state. We did an experiment with this where we used a persistent library called Ermin, which presents a Git-like interface for data storage. So what we did with this was we took a small part of the networking stack, which is normally buried way deep in kernel space, called the ARP table, which is just a link of IPv4 addresses to MAC addresses. The details aren't important. You can think of it as a key value store with an expiry time on it. And instead of just burying that in memory where we'd never be able to use it, we took that and we put it in Ermin. And something that's really nice about Ermin is that it also preserves history. And you can look at it basically like a Git store. So when we did this, we suddenly had access to the entire history of everything. When we ran our application, we suddenly had access to the entire history of all of the changes that had happened to this internal state. So we can, in live testing, we can run it either in memory or on disk. And when we run it on disk, we can just run git log on it. I'm going to show you a quick example of what that looks like. So we have automated updates from our expiry timer. I've run with --patch, but there are no changes here. If I scroll down a little bit, though, you can see eventually we can see the details of the changes that were made automatically to this process by our program. And when this is running live, you can also yourself in a terminal clone it, make a branch, update that branch, and commit it back, and watch your application react to those changes. This is really, really amazing for debugging. Something else that someone else in our group worked on was thinking about the scheduler. So we have, even in a unikernel environment, we have some things that might want to yield. We have a concept of different parts of our program working together because, for example, we're not always receiving new network data and acting on it. Sometimes we want to yield and wait for new things. Sometimes we need to wait for our own information to get out before someone else can react to us. In Mirage OS, we use lightweight threading for that. And someone said, well, it would be really nice if we could use a scheduler that kept a log of everything that it was doing and then showed us a really nice visualization of what was going on with our processes. So if you're interested in more information about this, there's a really excellent blog post about it with, I think, the best title I've ever seen. It's called Visualizing an Asynchronous Monad, which sounds just mystical and fantastic to me. But what it actually looks like when you visualize an asynchronous monad. Here's an example of one of the traces that we took from Mirage OS unikernel, which is it's a two-dimensional representation of all of the different tasks that we're running over the. You can't see it really in this view, but this is about 30-minute. This is about a 30-minute. There we go. Yeah, each grid division is 10 seconds. You can't really see the grid divisions, but they're very small. And we can see all of the different tasks, what they're yielding to. So basically what things are sleeping, why they're sleeping, what things are active, and when. So if I took this trace because I was trying to figure out why a particular application that I was running was taking absolutely ages and ages and ages to do anything useful. And it turns out it was waiting for a really, really, really long time to write an entire database onto the disk. And I can see that process right down here. It's taking absolutely ages. And then it finally completes, and other things can go on once it's done. Oops. So that's just a short summary of things that we've done so far. As I said, there are other library operating systems that are out there. This is just a short selection of ones that I thought might be interesting to the people in this room. There are more at unikernel.org. Sorry, we don't have libraryoperating-system.org. My bad. And most of the work that I've presented is not my own work. It's the work of the huge number of people that have contributed to Mirage OS and the huge number of academics who've worked on library operating systems and related concepts over the years. So thank you, everyone who did all the work so I could stand up here and talk. And also thank you to the European Union for giving me money. Thanks.
Hi, excellent talk.
Thanks.
I got in a really deep argument with our very grizzled sysadmin about a recent blog post called Unikernels Are Unfit for Production.
Mm-hmm.
Yeah.
Yes.
I was just curious on some of your thoughts and your counter-arguments. I think the thesis is that you don't have tools, traditional tools like dtrace that allow you to debug very subtle errors, and so I was curious on your take.
BSD also didn't have dtrace until someone wrote it.
That's right.
That's the short version of my argument.
Okay. So the idea is that you could do something like a dtrace in the library operating system.
I think it's actually easier to write really cool tools like dtrace.
Yeah, I would
Yeah.
see that. Okay.
Yeah.
So maybe your counter to that is like that might be a criticism now, but you're not looking on like future progress.
Yeah, and it's certainly true that we don't have the quality of tooling around unikernels and library operating systems that we would want to. Like there's still not a whole ton. There's not a whole lot of public adoption, although there has been a lot of private work that hasn't necessarily been open sourced, particularly around the HAL-VM. And this is a really great time for building something if you see its absence.
Okay.
Yeah.
Excellent. Thank you.
Thanks.
I kind of wanted to follow up along those same lines, but more about what this story is today about, like just in general, any sort of like live debugging, like attaching to something, poking around, seeing what's going on in there. Like, are there tools for that? I know a little bit about Mirage OS, so, but.
Probably the best thing that we have is the visualization engine that I showed you, which you can actually in real time get you can continually refresh those and get as the unikernel is running that expression. which is really cool. We don't have anything like GDB server at the moment, but there's a lot of really promising stuff around debugging going on in OCaml generally right now. So I'm really hoping for to have a better answer to your question in hopefully a couple months.
Awesome, thank you.
Thanks.
One of the things traditional kernels provide is privilege separation,
Yes.
so that when you make a system call, now you're in a higher privilege level. How does that work in library operating systems? You don't really want your database layer messing with your ARP tables, for example.
Right. So there are sort of two answers to that. One is if you're running everything that you generate with this within a separate virtual machine, you're then relying on the hypervisor to do that separation for you. And if you're running, for example, in a kind of traditional cloud environment, you'd have a hypervisor that's doing that for you anyway. So you've basically just eliminated a layer of unnecessary privilege separation that's not really separating any privileges for you. The other thing that I would say to that is something that we worked on with Ermin that I didn't really talk about is the fact that Ermin is type aware. And so so for example, you might have like a whole bunch of different state related to different things, and be able to, for example, branch and make some changes, but have some logic around what's merged back in that keeps information that might that some application logic says is a bad idea from actually being merged back in. That's a little wilder answer to your question. The more conventional answer is the first thing I said, but you can also do wild stuff like that.
Got a question down there.
Oh, thanks.
Yeah, I think you just answered that question, but let's get anyway. You mentioned that the API runs on top of a runtime. Does that runtime live independently of your application, or is it running as part of your application?
So it's built independently, but what you get when you build a Mirage OS unikernel is you just get a giant ball of virtual machine. So this is it ends up being constructed all together.
So you could have multiple instances of it running at the same time.
You would have difficulty with current tooling. You would have difficulty doing that. In theory, there's nothing that keeps you from writing your own like scheduling and running multiple virtual machines within running multiple runtimes within the same virtual machine. But you'd have to write all that yourself at the moment. And at that point, you basically have a traditional operating system. It's just one that you've written yourself.
Yeah, so this is a bit more of a random tooling question. So I'm a Haskell person. I haven't really used Mirage, but from what I understand, there's a big tendency to like write everything in OCaml, right? So for tooling, you mentioned debugging. Things like the reverse debugger work there, right? Can you use that like on a user space application, for example?
You should be able to.
Yeah, because you highlight something in a long time ago in earlier life. I used to like work on file systems, so I had to write file system implementations in like C, which is ridiculous.
Yeah.
And so
I'm a former C programmer. Sorry.
So you run into all these weird edge cases where it's incredibly hard to reproduce certain corruption bugs. And our software is really advanced. So the Ermin would be nice, but in particular it would be nice to I had all kinds of random cases where you write a block to an incorrect offset or something. So it'd be real nice if I could have a user space tool for reversing that. And we ended up writing all of that. Like we ended up writing a file system layer that could work in user space.
Yeah.
But so all that kind of tooling typically works like for the user space stuff.
We actually even have demonstrations for the case of file systems.
Oh, okay.
We have user space tests for some of the file systems that run on top of basically it's a virtualized block store.
Right.
Yeah.
Okay. Yeah. Cool. All right.
Yeah.
Thank you.
Just a quick question. So when you showed the either, I think it was an either, so that struck me like, okay, that's really great. So I was just wondering, culturally, did you find the community was going for more of these kind of total functions, or do you feel like, no, it's kind of depends on who's writing the library for Mirage. Sometimes you have to worry about exceptions, but most of the time not. Or, like what kind of, if I'm getting into this, is that my basic expectation that I can stop worrying about invisible errors?
At the moment, you can't stop worrying about invisible errors, I'm sorry to say. We're having a Mirage OS hackathon in March where I hope to push some people to make some API changes that will help with that problem.
Okay.
Yeah.
So it's moving.
It's moving. People have a lot of opinions, but there are more opinions than hours in the day, unfortunately.
Gotcha.
One more question.
Oh, thanks.
Probably a pretty basic question, but so the ability to write your own kind of operating system interface layer, is that predicated on the thing you're writing on top of itself having sort of a sane interface layer, the hypervisor, I guess it would be?
Yeah. So We're really lucky with Mirage OS because there are like a lot of the people who wrote stuff for Zen, the hypervisor that we target for unikernels, were OCaml people, and so we have nice OCaml interfaces for dealing with Zen. But you do eventually get down to a layer where like the thing just wants to speak ones and zeros, and whoever has done a good or bad job of implementing that, yeah, they've done a good or bad job of implementing that.
All right, thank you, Mindy.